Right, which of the following pair of solutions will form an alkaline buffer that best resists a change in pH, right? So when they highlight the word best resists a change in pH, when a small amount acid or base acid, they basically want one that gives you the maximum buffer, right? Maximum buffer. So maximum buffer, you must have an equal amount of weak base and a conjugate acid, yeah? Okay, let's look at option A. I'm just gonna do based on all of them. So sodium hydroxide will react with ammonium, right, to give you, so ammonium is actually a weak acid, so you get ammonia plus H2O, right? So let's calculate the number moles of sodium hydroxide. Is supposed to be 0.01, right, and the number moles of ammonium is 0.004. All right, okay, so I'm going to do ICF or ICF, okay, initial change final. So you can see that the sodium hydroxide is actually limiting, okay, so 1 to 1, so I put minus 0.001, this plus 0.001, okay, so in the end you have 0.003, this 0.001, right? So you still have ammonium and ammonium, okay, but they're not in equal amount, but you still have a alkaline buffer. Okay, let's try for B. Sodium hydroxide is reacting with CH3COO minus. Oh, this is a base, a weak base, and this is a base. So this one actually has no reaction. Okay, and this has no reaction. Okay, let's look at C. All right, you have H2SO4, which is a strong acid. It reacts with the weak base over here. All right. Okay, so in fact, this is how you balance it. Right, there's a lone pair and the N is actually a weak base, so but it's going to accept the H plus. So this is what you're going to get. You get 2 CH3 CH2 NH3 plus. Okay, so and then you have SO4 2 minus, so it's 2 plus and SO4 2 minus. Okay, so this is the salt. All right, so I'm going to put ICF. So the number moles of H2SO4, if you did the calculation nicely, right, you should get 0.01. The number moles of the weak base is actually 0.02, okay, from here. All right, so which means they will actually react very nicely. All right, they actually react very nicely. Minus 0.01, this one minus 0.02, because the ratio is 1:2, then plus 0.002. All right, so for this one, you in the end you only have the salt. Okay, you only have the salt, which just means it's not an alkaline buffer. Okay, let's look at the last one, which is option D, sodium hydroxide reacting with this weak acid. Okay, so you get CH3 NH2 plus water, okay, but plus Na plus, but actually the Na plus is really a spectator ion. Can? All right, so otherwise, if you want to keep it simple, then you put OH minus. Okay, myself just use OH minus. All right, strong base, and then take away the Na plus. Right, we can also do it that way. Okay, so anyway, what's more important, let's put in the values. So the number of moles of sodium hydroxide is actually 0.0025. The number of moles of this weak acid is supposed to be 0.005, right? So ICF. So I guess OH minus is the one that's limiting. This is 0.0025, this is 0.0025. So you look at the last line here, this is a weak base, so you have so much, and it's conjugate acid, which is the same amount. So in fact, this is your maximum basic buffer. So this is because you have an equal amount of weak base as well as a conjugate acid. Yeah, so this is the maximum basic buffer, is able to resist change in pH most effectively, right? So the answer must be D.